Hello, this is lecture 26, and what we'll do here is in the last lecture we saw the concept of frame and then just demonstrated in one example how the bending moment and shear force and axial force diagram for a frame can be drawn. This is a very short lecture where I quickly show you two examples, not go through the entire process of arriving the bending moment and shear force, not doing the entire calculations, but show you the examples and what are the final diagrams and how their deflected shapes are. The first example is, it is again a portal frame. Now there is one important part is here. We have one internal hinge here. This is a hinge here. Okay. So this is a frame subjected to uniformly distributed load 3 kilonewton per meter, 4 meter, 4 meter, 4 meter, 4 meter, and in addition to that there is an internal hinge. So this is A, this is B, this is C, D and E. There is an internal hinge at C. What you need to find out? We need to draw the bending moment and shear force diagram for this. Now, if you break the entire part into entire structure into two part and draw their free body diagrams, then free body diagram that will be something like this. Now, so this is hinge support. This will be AX. Let's use different pen. AX, and then this will be AY. Support reaction here is EY. Then we have externally applied load. This is 3 kilonewton per meter, 3 kilonewton per meter. Okay. Now draw the bending moment, draw the other. Now this is A, B, C, this is A, B, C, C, D, E. Okay. Now, so this is, suppose this is hinge. So there is no moment here at this point. So suppose this is CX and this is CY, and when we show CX and CY at C, it will, and C belongs to other part, it will be in opposite direction. So this will be CX and this will be CY. This is the complete bending moment, this is the complete free body diagram. Now if we apply the equilibrium equations, then what we have is AY is equal to 12 kilonewton, AX is equal to 6 kilonewton, and UY is equal to UY. This is again, this is also hinge. This is also hinge. So there will be EX as well. EX as well. EX is equal to minus 6 kilonewton, okay, and minus 6 kilonewton. EY is equal to 12 kilonewton, okay, and CY is equal to 0, CY is equal to 0, CX is equal to minus 6, and CX is equal to minus 6, okay, minus 6 kilonewton, okay. Now this is the complete support reaction and the hinge reaction that we know how to determine it using the equilibrium concept of equilibrium. Now let's draw quickly what is the shear bending moment and shear force diagram. Okay. Now you see again, let's draw the bending moment shear force diagram by looking at the frame itself without taking a section and then see, and then representing moment and shear through a function. Now between this is a symmetric part, and so and this point, at point C, the bending moment will be 0. Now and between at point C, bending moment is 0, and since between C and B it is it is uniformly distributed load, we know the bending moment varies quadratically, second order, and what would be the bending moment diagram, hogging or sagging. This part, if you state this is C is equal to 0, so this part will cause hogging in the beam, this part will cause hogging in the beam, right, hogging in the beam. So this will be negative bending moment, same as here. So let us draw the bending moment diagram here. So this is part C, where bending moment is 0. Okay. Now between C to this, as it can be seen that it is a hogging moment, and the varies quadratically, and this will be the bending moment between part C and B. Similarly, it is symmetric, so bending moment between other part will be like this. And what will be the this value? This value will be the, if you take this value will be the moment at B because of this entire loading on this entire length, and this value will be MB will be if you take this length is 4 meter, so 3 into 4 into 4 by 2, so this become 24 kilonewton meter. Okay, 24 kilonewton meter. So this is 24 kilonewton meter. So this value will be 24, this value will be 24. Now at B, if we draw the free body diagram at part AB and apply the equilibrium condition, we will see that MB is equal to 24 kilonewton, anyway we have obtained, minus 24 kilonewton we already obtained, and between these two there is no other external load. So at this point bending moment is minus 24, and at point A bending moment is 0, and between B to A bending moment varies linearly. So the bending moment between this to this will be varies linearly. Again, as per our sign convention, bending moments are drawn. Bending moments are drawn on the compression side. Okay. Okay. Now, so this is bending moment diagram. Bending moment diagram. Now, if I have to draw the shear force diagram, again find out the shear force. Shear force will be maximum here. This will behave as like a simply supported beam. This shear force will be maximum here. Then, since bending moment is quadratic, shear force will be linearly varying, and then shear force become this. Now, and what will be shear force here? The shear force here will be the axial force in this member. What is the axial force? Cx is equal to minus 6. Cx is equal to minus 6. So axial force in this segment will be the shear force for B. So the shear force for AB will be minus 6. So the shear force diagram finally becomes, again this is internal hinge, this becomes, and this becomes barrow, this becomes 12, this 6, this 6. This is shear force diagram. Okay. Now, you can take the section and draw the free body diagram and get the expression and draw the free body diagram. You can do that, but here just to show how the bending moment and shear force may look like for this member, just quickly see the deflected shape of this. The deflected shape of this will be this. Okay. Now, just quickly one last example. This is the last example. This is the last example. We need to draw the bending moment and shear force diagram for this. Now, remember in the previous class I showed you at the same joint you can have several members, not only two, you can have 2 members, 3 members. This is one example where you have 3 members. This is joint A, this is B, this is C, and this is D. The idea is draw the bending moment and shear force diagram. Now, let us first divide the entire, take all the members separately and draw their free body diagram. Now, this is member AB, this is member say member CD and say this is member CB, this is member CB, and then what are the forces we have here? This is, we have AX and then AY, this is, then we have BY, okay, and then externally applied load, say this on this, this is externally applied load here, this is 10 kilonewton. Anything else? All the external load are shown. Now let us draw the internal forces. Now internal forces are, now this is A, this is A, this is C, this is D, and this is B. Okay. Now the member C belongs to this part, and both this part. Okay. Now let's, this force is FCD, means it is the longitudinal force in member CD. This force is VCD and this MCD. Okay. This is the free body diagram of this, and then suppose for this case this is FCA and then VCA and then moment MCA. And if we draw for this part will be VCB and then FCB and then moment MCB. Okay. So these are the free body diagram of the same joint, but when it belongs to different part. Okay. Now why it is important? First is, you can, if you can draw the free body diagram of the entire structure and calculate the support reactions, right? That can be done. If we calculate the support reactions, then the support reactions are like this: AY is equal to -1 and BY is equal to 19 and AX is equal to 0. So this you know how to determine just by applying the free body drawing the free body diagram of the entire structure and apply equilibrium condition. So now look at this. Now we need to find out what is MCD, FCD, VCD and all these internal forces. But what we know, you see, there is no externally applied moment here. So what happens is, the summation of MCA, so what is the total moment at C? Total moment at C is MCA, MCD and MCB, their sum. So their sum should be equal to 0. So what we have is MCA plus MCD plus MCB, they all equal to 0. That is the equilibrium condition for point C. Okay. Now let us draw the free body diagram of this part. If we take moment from here, then we get MCD is equal to -20 kilonewton. MCD is equal to -20 kilonewton. Take moment from here, this force will contribute, this distance is 20, so MCD will be -20 kilonewton. Okay. Now you take free body diagram of this point, calculate the apply the equilibrium condition with summation of moment at this point. These two force will not contribute, this force will not contribute, only force will contribute MCB, and then MCB is equal to 0. MCB is equal to 0. So if MCB is equal to 0 and MCD is equal to -20, you need to maintain the support, maintain the equilibrium condition here. And what equilibrium condition says is the algebraic sum is 0. So these are not all plus. MCA is anti-clockwise, so this is negative. MCT is clockwise, positive, and MCB is anti-clockwise, so this is negative. So this has to be equal to 0. We know MCD is equal to -20, MCB is equal to 0. This gives us MCA is equal to 20 kilonewton. 20 kilonewton. Okay. Now, similarly you can calculate from this free body diagram, if you see there is no horizontal load. So, VCB will be equal to 0. Okay. MCB is equal to 0. Now, if you take this free body diagram and then apply summation of Fy is equal to 0. So, only forces are VCD and 10. So, VCD will be 10 kilonewton. So, VCD is 10 kilonewton. Okay. And let us find out VCA. Now, if we draw the free body diagram of this part and use the free body diagram of this part, apply summation of forces are is equal to 0, AY plus minus VCA, and this force will contribute. This force is known, AY is already known, and if you do that, then VCA will be I am not explicitly calculating it, but how to calculate, I am just telling you that, please verify these results. So, all these forces now we have determined. Okay, all these internal forces we have now determined. One other important point, see FCD is the axial force for this member, FCA is the axial force for this member, but the same FCB will be in the same, yes, but in this direction your shear force is VCB. Okay. Now, similarly, the way this moment at point the equilibrium condition is satisfied through moment, similar equilibrium condition can be satisfied through these forces as well. What it says that summation of all horizontal forces at point C will be 0. What are the horizontal forces you have? We have FCA, FCD and VCB. Now, from this free body diagram we have CD is equal to 0, VCB is equal to 0, naturally FCA is equal to 0. Another free body diagram, another equilibrium condition is all the forces which is vertical direction are 0, vertical direction 0 forces are VCD, VCA and FCA. We have already calculated VCD, VCA, and then FCB will be, we can calculate what is the value of FCB. Now, from this if we have to draw the bending moment diagram. Okay. Just draw this. So, bending moment will be 0 here, no, not this, I need another paper. Draw the bending moment diagram. So, bending moment will be 0 here at this point. So, between this point to this point bending moment will be 0, between this point to this point bending moment linearly varies and the bending moment will be hogging moment. So, it will be hogging moment, and then hogging moment, and for this there will be no bending moment, and for this bending moment is 0 here, and between this point to this point bending moment varies quadratically, and again it will be for this load actually this is hogging moment. Okay. So, this will be your bending moment diagram. This is bending moment diagram and this is bending moment diagram. This is 24. And similarly, if I have to draw the shear force diagram will be, you check yourself at this point, between this point to this point, shear force is 0, and between this point to this point shear force is constant, and that shear force will be 10 kilonewton. So, shear force diagram will be, here it is 10 kilonewton. At this point your shear force will be support reaction which is -1. At this point your shear force will be VC which is -9, that we have already calculated. Shear force will be this, shear force diagram is this. So, this is shear force diagram. Okay. Now, like this I have not done all the calculation, I have the calculation with me, I am just showing you the final result. Please verify these results and then see whether you are getting this similar shear force diagram or not. Quickly check the deflected shape. This is the deflected shape of the beam. Okay. Now, one important part is for the same beam supports, if I change this load, this load is 2 kilonewton per meter, but if I change this load to 2 20 kilonewton per meter, say 20 kilonewton per meter, but the same structure, same boundary conditions, but if this load is different, this load is 2 kilonewton and this is 20 kilonewton, you see the deflected behavior is completely different. I mean, they are deflecting in a different direction, okay, because now this load is more, so that see this load will produce some hogging, and this hogging will be balanced by this load. But if this load is small, this hogging will not be balanced, means this hogging will dominate and this beam will deflect like this. But in this case, this will produce hogging and this will produce sagging in the beam, but since this sagging load is, this load is more, the entire deflection will dominated by at this part, this sagging of this beam. So this is the deflected shape. Okay, so please go do some examples from from the books, and please make yourself comfortable with bending moment shear force diagram for frames. Throughout this lecture, we will be using extensively shear force, bending moment and axial force diagram for beams and frames. Okay, with this I stop here today. Thank you. Next class we will see how to find out deflection of frames using method of virtual walk. Thank you.